Welcome friends. So in the last class we have discussed the AC excitation on R individually, L individually and then C individually. There we have seen in case of a resistance current and voltage are acting in same phase, whereas in case of inductance current is lagging by an angle of 90 degree than voltage, and in case of a capacitance current is leading by an angle of 90 degree than voltage. These are the fundamental relationship, fundamental understanding as far as the AC circuit is concerned. Now we shall see what will happen if a circuit containing a mix between RL, RC or RLC, anything. So first we shall see series RL with AC excitation. So we this is our fourth point. This is our fourth point or fourth topic, AC excitation. If you consider this figure 10, we have a RL circuit series. Now across this R we measure voltage drop across resistance, which is VR, and across this inductance we measure a voltage drop across this inductance, which is called VL, and supply voltage is V. So we write this V must be equal to VR plus VL. V must be VR plus VL, but this summation is not a plain algebraic sum. They are all phasors, right? They are all phasors, so they are not the algebraic sum, they are phasor sum. So you must consider the phase angle. So now let us consider the phasor diagram first. So now what is phasor diagram? Now from the understanding of the previous cases that this voltage phasor, it is the the phasor diagram is nothing but you representing different phasor in a same diagram, under same diagram, where let us say for the capacitance we observe three diagrams till now. For resistance, for R, if this is V then this must be I, they are in same phase. For an inductor, if this is V then this is current I, and for capacitance if this is V then this must be current I. It should be current should be leading by 90 degree. For inductance current should be lagging by a 90 degree, and in case of a resistance current and voltage are in phase. So you are representing phasor diagram is nothing but you are representing different phasor in a same diagram. And most importantly, here phasor diagram is mainly drawn to understand or to illustrate the phase angle relationship between different phasors. Here magnitude is not important. It is not possible as well to draw in scales. However, phase angle it is drawn the relationship to show the relationship between different phasor in terms of phase angle. That means if you consider this diagram R, in case of a resistance, voltage and current is this phase. Here magnitude, voltage magnitudes and current magnitudes are not important, but what important here is that angle between them, that angle between voltage and current, this angle, it is zero. Angle between them is zero. Here inductor and capacitor, for these two, so here voltage magnitude and current magnitude is not important, but what is important here is that the voltage angle and current angle, this between is 90 degree lagging. Same way voltage angle and current angle is 90 degree leading, where it is not important at all to consider the magnitude. So phasor diagram is a diagram by which we can represent different phasor to show their relationship in terms of phase angle. So phasor diagram phasor diagram is a diagram by which different phasors can be represented to show their relationship in terms of phase angles. So this is the phasor diagram. So if you consider this phasor diagram of this RL, now if you try to draw the phasor diagram of this series RL circuit, what will happen? Now it is a normal practice. You see, for a series circuit, you know the current, this current is constant. So this current, this I is taken as the reference phasor because it is constant. Now from the diagram or from the previous knowledge of voltage and current, in case of resistance, you see voltage and current will be in phase in case of a resistance. So if this VR is voltage drop appearing across R, so this should be the direction of VR. It will be in phase with I. And similarly, VL is voltage drop across inductor. So this current flowing through the inductor must be lagging than this VL. So if this is the current I, then this should be the direction of VL. So here it is I, here it should be VR, and here it should be VL. This should be the phasor diagram. And you know, from this equation, VR plus VL, VR plus VL, VR plus VL represented by this phasor, this is V, it represents the supply voltage. And angle between supply voltage and current is called power factor angle. Angle between supply voltage and current is called power factor angle. So now if we represent if we now draw the mathematical equations, so from this we start. So what is VR? VR is equal to nothing but current into resistance, I into R. Plus, now what is VL? VL is equal to I into XL, because we have previously seen that if an inductor is there, it will provide an inductance of or reactance of XL. Here it is, which is equal to omega L. So if you take I common, now R plus now XL, now we are writing XL as J omega L. Instead of writing omega L, I am writing it as, instead of writing it as omega L, I am writing it as J omega L. Now where from this J is coming? Where from this J is coming? This is the question. Okay, so let us consider only this. Okay, now J is an operator. J is an operator. It should be, if we multiply it, in terms of phasor, suppose it is a phasor, right? A. Now if we multiply this with j, now it will become like something like this, ja. So that means j is an operator that gives a rotation of 90 degree in counterclockwise direction. In counterclockwise direction. So if this is A, it must be JA. It is rotated in this direction. Now if I multiply it with another j, so it will become j square. It will become j square. So it will be another 90 degree rotation. So j square actually means root under minus 1, it is whole square. So it will give you minus a. Minus 1. So when a is multiplied with j square, it is j square a, basically it will give you a minus a. So that is the meaning. So two j's are multiplied, that is 190 degree rotation, then another 90 degree rotation, which is minus a. That is exactly opposite. Now if you further multiply it, then it will give you j cube, another 90 degree rotation, and finally fourth rotation will give you the same phasor. So j is a operator on, if we multiply it with something, it will give a rotation of 90 degree in counterclockwise direction, that is positive direction. Now if you consider the phasor diagram, so that was the circuit for you. This is R, that is L, and this is your alternating supply V. What we have assumed? We have assumed current is same. So we take current as our reference phasor. Current as our reference phasor. So now VR, this voltage is VR. This voltage is VR. So VR should be acting in phase, and this voltage should be VL. Now current flowing through the inductor should be lagging. So VL must be in this direction. So current is lagging than inductive voltage. So if you draw the phasor summation, the supply voltage. So this is the our complete phasor diagram, and this angle between voltage and current is phi, which is called power factor angle. So now what is VR? VR is equal to, here VR is equal to I into R. What is VL? I into XL. Now what is XL? What is XL? I into omega L. Now if you multiply, it does not make any sense, because you see with respect to the reference phasor, it is rotated by, that is very important. With respect to the reference phasor, it has taken a rotation of 90 degree. With respect to reference, it is taken a rotation of 90 degree. So it is a J rotation by an angle of 90 degree. So J 90 degree rotation, it represented by J. That is why a J comes in the, in the expression J omega L. So we write V is equal to VR plus VL. VR is equal to IR, and VL is equal to I into J omega L. Why this J in just to understand or just to illustrate the 90-degree rotation. So from there, if you take I common, so in the bracket we have R plus J omega L. R plus J omega L. So if you have R here, then J omega L should be along this, because J is represented by a 90-degree rotation and the phasor summation of these two is represented by Z, where Z is equal to R plus J omega L. It's called impedance of the network. Impedance of the series RL circuit. And if you compare this with this diagram, so it should be phi. This angle should be, you see, VR is IR. Okay, VR is taken in this diagram or in this direction. VR is equal to I into R. Now VL is 90-degree leading, so if you take VL in this direction, so this is VL, which is equal to I into J omega L, and this is supply voltage V. V is equal to I into Z. Now with respect to each term, it is V is equal to IZ, VL is equal to IJ omega L, and VR is equal to IR. You see, this I is common everywhere. I is common everywhere. So if you can take out this I, that by dividing V by I both the sides, so in the x-axis it will only R, in the y-axis it is only J omega L, and in the resultant is only Z, which is equal to R plus J omega L. So R here is for resistance, J omega L is equal to XL, and Z is the impedance of the network. So Z is equal to, when we say Z is equal to R plus J omega L, it is called impedance of the series RL circuit, and its magnitude is given by R square plus omega L whole square under root, and angle is tan inverse omega L by R. So this is the magnitude. This is the magnitude, and this angle is nothing but phi. This angle, it is tan inverse omega L by R. So we are, so what we have observed here, that we have observed first series RL circuit, and we have drawn the phasor diagram for this VR, VL and V, and from there we got this triangle consisting of all impedances. It is called impedance triangle. Impedance and from there it is established that Z is equal to R plus J omega L, whereby we can say the magnitude of impedance is Z bar, which is equal to this R square omega square L square under root, and phase angle is tan inverse omega L by R. That is the power factor angle. So now from the phasor diagram, we can write that. Now please consider, for the time being, we have started by assuming that current is my reference phasor. That's all right, very right. But we have ended up by something like, if this is current and this is supply voltage and this angle is phi. Now for the time being, now let us consider the supply voltage is the reference, then current is not reference. So now if you write the supply voltage as V is equal to Vm sin omega t, so this current must be written as Im sin omega t minus phi. So here current is lagging by some angle of phi, which is not 90 degree this time, but it is lagging by some angle of phi, by some angle which is phi. The range of phi is equal to 0 to 90 degree. It can take any value depending on the value of R and L. Depending on the value of R and L, it can take any value. If R is more, phi will be tends to take closer to 0 degree, and if L is more, then which means phi most likely to slant or tilt near 90 degree. This is the meaning. If R is dominant over L, you see this expression, if R is dominant over L, so this will give you the low value, so phi will be near to 0 degree, or less value, it will be tilting towards 0 degree. And if L is more, then this numerator will be large, so it will be tilting around 90 degrees. So depending on the value of R and L, the phi will be taken in between 0 to 90 degree. But this is the overall relation of voltage and current in case of series RL circuit. If V is Vm sin omega t, then I can be written as Im sin omega t minus phi. In general, we can say current in a series RL circuit, that is a very important observation, current flowing through the series RL circuit is lagging by an angle of phi. That phi should take this value. It means phase displacement between voltage and current is phi. Now what is that displacement? It is always lagging because current is lagging. Now coming to the power. Now instantaneous power is given by V into I, what we have observed previously. So V is equal to Vm sin omega t, I is equal to Im sin omega t minus phi. So we do like this, 2 sin omega t minus phi. So it is a formula of 2 sin c sin d. So it will be first term will be cos phi and second term will be cos 2 omega t minus phi. So this is the formula. Instantaneous power Vm Im by 2 cos phi minus cos 2 omega t minus phi. Now if you integrate this expression, E is equal to total power, that means Vm Im by 2, it should be 1 by 2 pi integrate 0 to 2 pi cos phi minus cos 2 omega t minus phi, cos omega t minus phi. So now if you integrate this with respect to d omega t, so now this term is already been discussed, it will be V RMS into I RMS. Now as far as this is concerned, it is state 0 because it is a cosine function of time. So it will be cosine function. So integration over a complete cycle is 0. simple, so this will be 0. Now as far as this term is concerned, so the integration of this cos phi d omega t is, it will be cos phi taken outside. Now this 1 by 2 pi comes here. Now d omega t, that means omega t, and if you put the limit it will give you a 2 pi, so this 2 pi cancel, so power becomes v into I cos phi. Very important relation. Power is equal to v into I cos phi. So this is the expression v into I into cos phi. This v and I is the RMS value. This v and I are the RMS value. Now phi is the called, it is power factor angle. Now power consumed in case of a series RL circuit is given by equation 15, which is VI cos phi, which is VI cos phi. So now if I say this is power factor, what is the definition of power factor? This is very important term. Power factor is defined, it is the cosine of the angle between voltage and current phasor. It is the cosine of the angle between, you see this diagram, it is the cosine of the angle between voltage and current phasor. Is the cosine of the angle between voltage and current phasor. However, we have a condition that voltage and current phasor must have the same frequency. It should have the same frequency. So what will happen if the frequencies are different, we shall discuss later on. So this is the definition of power factor. It is the angle between voltage and current between the power factor. So the ranges of power factor is between 0 to 1. For purely resistive circuit, cos phi becomes 1. Why? Because we have already mentioned here, in case of a resistance, yes, you see power factor is unity. Why? Because voltage and current are in same phase, so the phi is 0. So phi is 0 means what? Cos phi is 1. That is why power factor is always unity in case of a purely resistive circuit. And in case of a purely inductive and capacitive circuit, since phi is 90 degree, so cos 90 is 0. That is why power is not dissipated in inductor or capacitor. And the nature of the power factor is lagging for series RL circuit. It takes this value. So to briefly recap, we have a series RL circuit. We have VR and VL, voltage appearing across resistance and inductance, VR and VL. We have drawn the phasor diagram first. Current, we consider it was a reference phasor I. Then VR should be drawn in phase with I because it is the resistive drop. Then we have drawn VL 90 degree ahead of current. Then using this equation, if we sum them by phasor means, we shall get V by this in this direction, and the angle making with the current phasor, it is phi. So this phi is called power factor angle. and from there we have got an impedance triangle where x-axis is represented by resistance, y-axis is represented by inductive reactance, and the summation of them is z. So z is nothing but magnitude, if you consider it is root under r square plus omega square L square, and this phase angle phi represent tan inverse omega L by r. Now from the phasor diagram, if you consider, if you write V is equal to Vm sin omega t, which is reference, I must be lagging. As per this diagram, it is lagging by an angle phi. So I must be written in this fashion, omega t minus phi. So from the conception of leading and lagging phasor, we can understand that phi is the lagging current, or phi is the angle by which current is lagging than voltage. So from the current power equation, we have evaluated that total power is Vi cos phi. So what we have studied previously, if R was there, then power is V into I. If L is there and C is there, there should not be any power. However, in case of R and L is there, now this power is given by Vi cos phi. That is why it is called power factor. A fraction of power is available. Due to this term, a fraction of power is available. It is scaling the power. That is why it is called power factor. The range of power factor is from 0 to 1. What is the definition of power factor? It is the cosine of the angle between voltage and current with same frequency. And in case of a series network, since the phase displacement of voltage and current is 0, that is why it is only V into I in case of a purely resistive network. So we have seen the behavior of series RL circuit under AC excitation. So we are stopping here now. From the next class, we shall start the next topic, that is what will be the response of series RC circuit in case of alternating response. Thank you.